Okay, all right. Finally here. So let's explain what a monad is. Okay. All right. Let me increase the size of this. Wipe it off. All right. First example, as usual. So we have, let's say, a function at one. Oh well, at one. That's a function different than before. Before we have a to a plus 1, right? But this time we have a plus 1 inside an array. Okay. So let's examine the type for this. It's at 1 number to array of number. Right? Okay. Now I have a array of 1, 2. I want, if I only have these available to me, I want to add 1 to 1 and 2. Well, the first approach to use map, right? Because it's a functor. So I do map at 1. Okay, just quickly, what does this one give me?
2, 3.
2, 3?
2, 3.
Is that correct?
No. A array of array 2.
Array 2.
And array 3.
Okay. Okay. All right. Same problem as before, right?
Yeah.
If you want to add another, add 1 again, you will do map at 1, which adds another layer of array inside. Which, like what we did for the last example for the fetching stuff, one of the layers we have like 2 maps which operating on the same functor here. So here you're looking at 2 functors that contains value. That is a if I generalize array to a functor, that means a functor of number. Okay, so to make this problem, the map problem to access the value here, go away, we need something of this type signature. We need, like map, let me just reiterate again, what's the type signature for map? The function. Map. What does map take first?
Function.
A to B and FA, FB, right? Okay. All right. Okay. So now we need something to make these 2 go away. That means I need something here, which is a function as well, but this function is at 1 becomes FB. Right? So it's take a number, produce a number inside the array. So that's adding a context into that. So produce a functor. And then the second parameter would be FA. And I don't want FFB. Right? I want FB so that later on I use that, I don't need to map. All right. So we call this function the chain function. I'll get to why it's chain. So in the sense of getting rid of this map thing to operate on this kind of structure, we need a function like this. Normally, we denote the f not as in f, but n. Okay. So n is a monad. Okay. If it's specified, if you can find a function operated like this on a particular functor, then this n, which is a functor, is also a monad. Okay. The relationship between the things we're talking about before is functor, and then you have applictive, and you have monad. Right. Here is you have map available, you have of and AP available, and then you have chain available. Okay. So to solve this, very important. There's multiple ways. It's very usually like very common in function programming. When you look at a particular problem, you have a solution, and if that solution is general enough, then you can look at that solution, switch your view to another type of problem. You can apply that same solution again. So let me change the point of view on this monad, so we can have a look in a different light. But before that, there is in most functional programming languages, there is another method required actually. It's called return. In Haskell, return is A to MA. This is just of, right? Because every single monad is an applicative functor. So this is just of. But just remember, this is a bit of a historical problem. They discover monad first, after functor in Haskell. And then they discover applicative and put into language. So, this exists first. And then they say, okay, this thing should be on the applicative. That's the reason. When people talk about monad, they may refer to these two functions. Okay. Interestingly enough, if I give another function here, which what it does is this. Then you can look at those two as a definition of monad. Because here we're solving this problem, right? Essentially here is the same thing. If you have a function of two layers of same, very important, same context here, same functor, and you can collapse them into one, then you're looking at a monad as well. So, do you know what's the function called? I can't remember this. Union? Or no? Let's just call it union. I'll might give a different name next time, but I can't remember. Now, why I'm giving you this function as well? That's a very important intuition. What does monad do? It collapses context. Here is doing, because map lift, remember 2 weeks ago I think, it lifts this function to work into that context, right? So here, that's because the signature for map, so it's easy to compare them to. The difference is just that. Now here, it gives you different intuition of monad is to collapse the context. If you compare this to monoid, there's a very interesting discovery. you can find. Remember monoid. We have a M empty, right? So it's just a empty value, right? It's a unit, and then you have a binary operation, which a, right? Okay. When you look at monad, these two, right? On the type level, essentially we're doing n to n. Right? Okay. That means if I put something here to say a context, a functor context operate with the same context, produce one layer of context. If I say that like this, it is very similar to this. I have A, I have M. Very similar, right? I'm not saying they're the same, but it's very similar. Here, A to MA, it's also very similar because, how do I say this? Remember, we have an ID functor, which just contains the value, and when you map it, it just called a function. There's no particular functionality to it. Then it's like this, right? It's isomorphic. ID A is isomorphic. One can convert to the other, basically. Now this part, here we ignore A, we get this. If we ignore A here, we have a single value singled out with that. Again, these are very similar in a way that M is in the position of A, like that. So monad, in a sense, is a monoid, but in different construct, in different category, in category theory. You will hear, when you Google it, you will hear people say monad is a monoid in monoidal category of indofactors. That's what it means. That's what it means to say they are actually very similar, just in different worlds. This is another intuition you will encounter later on when you Google it. That.
I think the unit should be join.
Join, okay. Join. Yeah. That's the another way to look at monad. Let's have a look at another way. Let's get rid of this so we don't need this functor stuff. Okay. What if you have two functions like this? Look. Oh, that's good. Okay. What if you have two functions like this? A to MB, B to MC. And then I'll just write some function here that without context. Here, in order to compose those two functions, it's straightforward, right? F and G, you just A to B, call F first with particular A, and you call G out of it, right? And you do compose F first, G after F. Okay. You can't compose this like that, right? Because it's context. What you can do, back to the the multiple layer of functor, you have to map it. Right? So if we have A passed in here, if that's F, that's G, and when you call F, it produce MB, and you need to map it. And here you two-level context. Okay, that is a function called compose K. That saves you essentially allow you to do this and does the thing for you to give you only one level of context. It is equivalent to say, I don't use compose K, I use compose. I don't use map here, I use chain here, right? Because chain can, chain does this, right?
Yes.
Yeah. So here you get MC out of the two lines. The compose K just saves you the typing of chain. Now the requirement again is those two functions produce the same context. If this one produces list as context, this one produces maybe, doesn't work. Okay. Needs to be the same context. All right. What does this mean? It means monad gives you composition over this kind of a function. We call this kind of function and to look it up. How do I spell it? Classly.
K-E-I?
K-L-E-I?
Yeah. S-L-I.
S-L-I.
Yep.
S-L-I.
S-L-I. Okay. Classly. Arrow. A-R-O-A-W?
Yeah.
O-W? Arrow.
Arrow.
O-W?
O-W.
Yeah. Oh, okay. Okay. A classically arrow is you have a value and you produce another value in the context. So when you see this kind of signature, you know you need monadic composition. So that's already a third way to look at monad. Okay. We'll have a look at notes. All right. Right. Let me give you a fourth way to look at it. Still this. Now, let me put a concrete type here. Let's say this is a promise. Promise. By this, what you mean is, given a value first, it will do a computation, but the computation result in a side effect later on when you fork the promise, right?
Yeah.
And that give you a value in context. That's one computation. Based on that, based on that, right? You continue your computation with this function. Have another computation which produce the same context, in the future when fork it. So in a way, we're saying we're providing a continuation of computation. That's the fourth way to look at it. Okay. Is a fifth way? Okay. The fifth way is just a note. Because many people associate a monad with effects, especially side effects. What does it mean? Is actually, it's not the same with monad. It's actually functor represents this, right? If you have a functor, you can construct that function. Right? And it's not always side effects because, for example, array. 1, 2, right? It's a context, but doesn't. When you look at it as a container, it doesn't have an effect. But when you look at it as indeterminism, then it can qualify as an effect. Why is that? Let's say you want to generate a random number out of that array. Then what does that container represent? Indeterminism. It represents all the possibilities. Right? If you can construct a monad onto that, or functor onto that, then you can generate multiple random numbers. One depends on the other. Maybe you get a seed number in, you get an array of random value generated. And based on that, you can, for each random value, you can generate another bunch of random value. But you don't want two level of context. You just want one level of indeterminism. Then there you go. Yeah, this fifth way to look at it, it's handling effects. So in reality, for this course, what we're going to do is, of course, you're going to remember the type signature again, which is not here. Just one slightly change of map. The function first becomes a class arrow. Yeah. And Fantasyland give you the definition of monad like this. It needs to be a applicative and needs to be a chain. A chain is this. A chain gives you a chain method on it, which is that type signature. It just has these two reverse, right? This becomes the first and MA becomes second. And the chain function. Then this is the method. Yeah. And monad itself, because chain, it implements the apply specification. It has an AP method on it, but it doesn't have an of. Monad is applicative, so you have the of method on it. So you have of and chain, so it becomes a monad. This is very common condition you need to remember. I just say it here. So this law, it's called left identity. What it does is you put a value inside a monad. Okay. Well, it's applicative, but inside a context. Here we're talking about monad, so it's monad. And you produce, you have a f into that chain, then this actually equivalent to fa. Thinking about chain is reducing context. Right? So whatever f you pass in, it will reduce one level of context, so it's just equivalent to FA. Yeah. Okay. And any monad chained off function is just itself. That's the right identity. To demonstrate. Get rid of this. What does it mean concretely?
So this f here is just a function, right? Chain takes a parameter of f. Is that just a function?
Which one?
First one, yeah, the first one there. The chain f, is it f?
F is a function, yeah, just a function. And we don't care actually what function it is. So that means so array of 1, if it's a monad has a chain method on it, you pass a arbitrary f, it will be just f1. How do I say this? If f is, then the result will be correct. Because that's, yeah. If you dot map, that will be reduce one level, becomes that, equivalent to that coin on that. Okay. That's the one of them. Second one. What's the second one? What's the second one we're looking at? Okay. M chain M off. Yeah. If it's a map, then you're looking at, array of here, it will be if it's a map, array of, so 1 becomes 1 in the array, with that array 1. Yeah. Become a chain, reduce 1, context becomes, what is that? That is that calling with 1. So that's the two laws, just concrete examples. With that in mind, I have like a bunch of implementation we need to do, but we save a bit of time here. Just skip that. If we have time next time, we'll talk about that. For this, let's examine again what we have. See these two x's here. There's two maybes, right?
Yeah.
Yeah. Where does it coming from? It comes from the safe path. What's the other one? Safe prop. Is it? Or I don't know. Let me have a look at the.
Yeah, same for.
Yeah. Okay.
Maybe.
Right. So string. Let me just get it on screen. Okay. Yeah, it's 2 level just here. And the sequence already reversed the sequence. We have just a maybe array maybe. Right. Now, because of the sequence, we reversed the maybe and the array. So now we have actually two same functors next to each other. Right? Maybe list instead of maybe list maybe. Okay. Yeah. So that means the first map dealing with the promise, the second map dealing with that. And the third map dealing with that maybe.
Should go start with the get mode?
Sorry?
Should start with the second line. No.
Huh?
No.
Okay. All right. So dealing with this maybe. Remember, before the sequence produced this, right? Okay. So sequence produce a value in the context. Okay. The context is actually the same as the context before. So this map dealing with this maybe can actually be compressed.
Yeah.
So it will become one level of maybe. Now that means you still have, if you don't fork it here, you still need to reach the array here, you still need to write 3 maps. You can't reduce them because they are all different contexts. Okay. Now next time, hopefully, we're talking about how do we deal with that. But here's basically how to reduce levels of same context. Yeah. All right. So I guess we stop here for today. Yeah. Thanks.
Thanks.